Okay, so in this lecture, let us discuss the implementation of Boolean function using multiplexers. Okay, now in one of the previous lecture, we have discussed a decoder can be used to implement the Boolean functions, right? So we took a decoder and we implemented the Boolean function. Okay, so you take a decoder by using some external OR gates. So this combination is used to implement the Boolean function. And if you look at a multiplexer, as I said in the previous lecture, that the multiplexer essentially contains a decoder plus the OR gate and plus some selection inputs or inputs, data inputs. So if you combine these three things, then it becomes the multiplexer. Therefore, naturally this decoder produces min terms. So the output of the decoder is nothing but min term. Okay, so the min terms of a function are generated in this multiplexer circuit also. Now the individual min terms can be selected by the data inputs. Okay, so you take the data inputs and selection lines and you can select the min terms. Okay, so that you can implement the Boolean function. Now as I said, for multiplexer you have 2 power n input lines and then there are n selection lines and one output lines, only one output line. Now in order to implement a Boolean function, I have a Boolean function and let's say this Boolean function has n variables, 1, 2 up to n variables. In this n variables, what you do is you take n minus 1 variables for selection input. Okay, so the first n minus 1 variables of the function are connected to the selection input of the multiplexer. The remaining single variable, right, which is given to the input of your multiplexer. Okay, so the remaining single variable of the function is used for the data inputs. So this is data input and this is selection input and only one output, right? Now if you take a Boolean function, the Boolean function contains n variables. Out of this n variables, you take first n minus 1 variables which is given to the input of your selection input of your multiplexer, and remaining one variable, the last variable, is given to the data input of your multiplexer. Okay, now if the single variable is denoted by, let's say, z, for example, my function Boolean function is w, x, y and z. Let me take a 4 variable Boolean function. In that, these 3 variables I am going to give it as the selection input, and this last variable is given to the data input of the multiplexer. Now to demonstrate this procedure, it is better to consider a simple example so that we can understand slightly in a better way. Now let me consider a Boolean function. This is, let's say, f of x comma y comma z, only 3 variable Boolean function. So this is going to be summation of 1 comma 2 comma 6 comma 7. Okay, so the function of 3 variables, this can be implemented with them. How many input multiplexer do I need? 4 variables, I0, I1, I2, I3. Why only 4 variables? Because if you take n variables Boolean function, out of this n variables, n minus 1 is given as selection inputs. So 3 minus 1, 3 minus 1 is 2. So therefore I need two selection lines. Let me call these two selection lines, let's say S1 and S0. The X is given to X1 and Y is given to S0. So remaining one variable is there, that one variable is Z, and this Z is given to this data input. Data input, selection input. So this is a procedure and only one output F. So therefore, since I have two selection lines, the number of input lines are 2 power 2. 2 power 2 is equal to 4. Right? So this is 4 by 1 max. Now let us put the combinations. So as you know, you have two inputs, S1, let me write on S1 and S0. So you have all combinations, right? 0 0 0 1 1 0 1 1, right? 0 0 0 1 1 0 1 1. This is S1 and S0. The output will be, F is going to be I0, I1, I2, I3. So this is general operation of our multiplexer that we have already discussed in the previous lecture. Now I don't want this truth table, but what I need is, I want to implement this Boolean function 1 2 6 7. So 1 comma 2 comma 6 comma 7, I want to implement this. So since I have functions which starts from 0 goes up to all the way 7, I need three variables. Let me call those three variables X, Y and Z. So there are three combinations, 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 1. So it's 8 combinations. Now my output is going to be, this is 1 2 6 7. Okay, 0 1 2 3 4 5. Oh my god, 1 1 0. This is 6 and 7. 1 1 0. Sorry, 1 1 1 1. Okay, now wherever you find the function, Boolean function, there you put 1. So this is F of X comma Y comma Z is equal to summation of this one. So for this one you put the output is 1. For 2 the output is 1. For 6 output is 1. For 7 output is 1. Right? Rest of the places output will be 0. I don't want those min terms. I want only these 4 min terms. Remaining 4 min terms I don't want, so that's why I kept a 0 here. So up to this point, no doubt. So I have function of 3 variables, and this 3 variable function can be implemented with the help of 4 by 1 multiplexer. Now you take these 2 variables X and Y. This X and Y is given to S1 and S0, your selection variables. Okay, that means X is connected to S1 and Y is connected to S0. Now in the multiplexer, this part is over, this part is over. Now what should I give to I0? What should I give to I1? What should I give to I2? And what should I give to I3? Such that this function is implemented. That's what we are going to find out now. Okay. Now when the input is 0 0, output is 0. Look at here. I don't want this first minterm, 0th minterm. Again, when the input is 0 0, the output is 1. That means what? You look at carefully. This 0 is coming as 0 here, no change. And this 1 is coming as it is, no change. Therefore, when z equal to 0, the same 0 is appearing in the output also. When z equal to 1 here, the same 1 is coming here also. Therefore, this combination I need to apply z. Okay, so the output is nothing but f is equal to z. Therefore, whatever the c contains, that is coming in the output. The 0 is coming here as it is, this 1 is coming here as it is. Therefore, whatever the binary variable z takes, that is coming to the output. That is why I have written f equal to z. Okay, so this is one combination. Now here also 0 1 and here also 0 1. For this combination, this 0 becomes 1 and 1 becomes 0. That means it is inverted, right? So when z equal to 0, then it becomes 1. When z equal to 1, then it becomes 0. Therefore here my output is nothing but z bar. Now take next two combinations 1 0 1 0 1 0. For this combination, for this selection input, 0 comes as 0 and 1 comes as 0. So now how will I choose in this? And moreover my output is 0. Whether z equal to 0 or z equal to 1, my output is 0, isn't it? See, if you look at this combination, this is 0. When z equal to 0, when z equal to 0, my output is 0. Again when z equal to 1, again the output is 0, right? So irrespective of the z state, z value, my output is always 0. Therefore here I can write output f equal to 0. And then next take 1 1 combination. For 1 1, if you apply 0, my output is 1. If you apply 1, again also my output is 1. See, when z equal to 0, output is 1. When z equal to 1, output is 1. Irrespective of the value of z, my output is always 1. Therefore in this condition, output is always 1. So therefore for 0 0 combination, my output is f equal to z. For 0 1 combination, output is z bar. Okay, I told you how this z bar comes and z comes. And here 1 0 and here also 1 0. For this 1 0, my output is 0. Therefore f equal to 0 here. And 1 1 and here also 1 1, my output is always 1. Now we know that for 0 0, in this map, if you look at for 0 0, which one I am choosing? I am taking I naught to the output for 0 0 combination. 0 0 combination, I am taking I naught. Therefore let me erase this highlight so that you can understand in a better way. I have scribbled so many things. Fine. Now look at the map now. For if the selection inputs are 0 0, then I naught gets a path from input to the output. That means what? This is 0 and this is 0. In that case, I naught comes to the output. What is output? Output is z. Okay, that means what? The input is z. Therefore, I naught is connected to z here. Now, when the selection line is 0 1 and 0 1, then the output is z bar. So therefore, if the input is 0 1, then this I1 is coming to the output. But in the output, it is z bar for 0 1 combinations. Therefore here you put z bar. Now if you take 1 0 and 1 0, if the selection line gets 1 0 1 0, then your I2 gets the connection between input to the output. But when 1 0 1 0 condition occurs, my output is always 0. Therefore the 0 transfers to this point. Now take this last combination 1 1. If 1 1, then if the selection inputs are 1 1, then I3 gets connection to the output, right? So my output is 1. Therefore if I3 is 1, this same 1 would have appeared here. Therefore this is equivalent of saying 1. That's how you will decide the input of your multiplexer. So I have a 4x1 mux and 2 selection lines S1 and S0, If 0 0, you are choosing I naught to the output, yes or no? I naught to the output. Now in the output, see when the combinations are 0 0, what is there in the output? Z. Therefore this I naught is equal to Z. So wherever you find I naught, there you put a Z. That's it. Now when the selection inputs are 0 1, then I1 gets the path to the output. Therefore my output F is I1. Now if you look at the truth table, for 0 1 combinations my output is Z bar. Therefore for I1 you connect Z bar. In case if you give 1 0, then this guy gets output gets I2. Therefore I2 gets the path to the output. But 1 0, if you look at the combinations for 1 0, my output is 0. Therefore for I2 I should give to the 0 input, because I2 is always 0. My output is 0. For this 1 0 combination my output is always 0. So that is why in the input it becomes 0. Similarly you can write I3 is given as 1. That's it. So this is how you implement the Boolean function using multiplexer. Okay, so the general procedure for implementing any Boolean function of n variables, function of 1, 2, 3 up to n variables, with a multiplexer of n by 1 selection inputs and 2 to the n minus 1 data inputs. This is data input and n by 1 selection input and 1 output. Okay, 1 output follows from the the way we implemented in the previous example. Okay, so in this case the first n minus 1 variables, look at here, we have if you look at here x y z, right? You have f of x comma y comma z. In this first n minus 1 variables or 2 variables are applied as s1 and s2, s1 and s0 as selection input lines, and the L as the least significant bit, that is applied as the data input. Now let us take one more example. Let me take f of a comma b comma c comma d is equal to summation of 1 comma 3 comma 4 comma 11 12 13 14 15. Now again write all the combinations a b c d, and before that how many variables do I have here? 4 variables. So if you have 4 variables, then 4 minus 1 variable you have to take, that is 3 variable, right? So therefore your multiplexer size is going to be 3 by 2 to the power 3. Okay, so 3 by 2 to the power 3 means 3 by 8 mux. So how many selection lines do I need? 3 selection lines. So those 3 selection lines are S1, S2, S1 and S0. And this D is given as the data inputs that we need to find out from the truth table. Okay. Now this is my F. You put all the combinations 0 0 0 0 0 0 1 0 0 1 0 0 0 1 1, then 0 1 0 0 0 1 0 1, then 0 1 1 0, then 0 1 1 1, then 1 0 0 0 1 0 0 1, then 1 0 1 0 1 0 1 1 1 1 double 0, then 1 1 0 1 1 1 0, then all 4 ones. So this is the combination. Now this is 0 1 2 3 4 5 6 7 8 9, then 10 11 12 13 14 15. Now look at the function. For 1 the output is 1. These are the min terms I want. Okay, these are the min terms. That min term should be logic 1. So for 1 the output is logic 1. For 3 the output is 1. For 4 the output is 1. Then afterwards 11 12 13 14 15. So for 11 output is logic 1, 12 output is 1, 13 output is 1, 14 output is 1, 15 output is 1. That's it. Now rest of the combinations the output is 0. You fill it up 0. And here also 0 and here also 0. That's it. Now look at the combinations. Before that, let me draw the multiplexer. Here I0, I1, I2, I3, I4, I5, I6, I7. There are 3 selection inputs: S0, S2, S1 and S0. Here I am giving A, B, C. Okay. Now if A, B, C equal to 0, 0, 0, then I0 gets the path to the output. Right? I0 gets the path to the output. Now what is I0 in this case for 0, 0 combination? Look at here. So this is 0, 0 combination. In this combination, look at here, the 0 comes as it is 0 and 1 comes as 1. Therefore, that means what? If D equal to 0, the same 0 appears here also, in the output also. If D equal to 1, here also 1. Therefore, in this combination, F equal to D. Now, take this two combinations, 0, 0, 1. If A, B, C equal to 0, 0, 1, then your I1 gets a chance to the output, right? Therefore, in this combination, your F output is equal to, what is output? 0 becomes 0 and 1 becomes 1. No change of your D value. Therefore, F is equal to D. There is no change. If D equal to 0, here also D equal to 0. If D equal to 1 here and here also D equal to 1. Therefore, F equal to D. Fine, that's it. Now take this combination 0, 1, 0, 0, 1, 0. If the input is 0, 1, 0, then I2 get a chance to the output. Okay, therefore, in this case, 0 becomes 1 and 1 becomes 0. Inverted, negated. Okay, so the D is negated in this case. Therefore, your F is equal to D bar. And now here 0 becomes 0 and 1 becomes 0. Irrespective of the value of your D, the output is always 0. Therefore, F is always equal to 0. For which combination? For 0, 1, 1 and 0, 1, 1. In the selection lines, if you give 0, 1, 1, it corresponds to which input, which data input? I3. Therefore, when I3 gets a chance to the output is always 0. That means what? I3 equal to 0. That's it. Okay. Therefore, here F equal to 0. Now, notice here for take 1, 0, 1. If you give 1, 0, 1 here, 1, 0, 1 corresponds to what? 0, 1, 1, 1, 0, 0. I forgot two more. Yeah, I forgot this one. 1, 0, 0. And here also 1, 0, 0. Okay, so both are 1, 0, 0. So that means what? You are taking the input I4 to the output. Right? That means you are connecting I4 to the output, isn't it? Therefore, For 1 0 0 combination you are taking I4. So in this case, yeah, this is 1 0 0 and this is 1 0 0. So in this case I4. Now this 0 becomes as 0 and 1 becomes 0. Whatever the input, okay, whatever the condition here, 0 or 1, the output is always 0. Output is always 0. But the combination is 1 0 0. In this case 1 0 0, in this case I4 is connected. But for 1 0 0 the output is always 0. So I4 is always 0. That means in the input you are giving 0 here for I4. Now take I5 1 0 1. Now again look at the beauty here. See, the 0 comes as 0 and 1 becomes as 1. That means when d equal to 0, then output also 0. When d equal to 1, output also 1. That means what? It implies f equal to d. Therefore, this 1 0 1 corresponds to I5. So the I5 gets the value of d. And then you take 1 1 0 1 1 0. So for 1 1 0, if you give 1 1 0 as a selection input, then I6 gets a chance to the output. Now for 1 and 0, the 0 becomes 1 and 1 becomes 1. So the output is always 1. Always 1. That means f equal to always 1. But in this condition, when the output is always 1, when the input combination is 1 1 0. That means what? When the input combination is 1 1 0, then I6 gets a chance to the output. In that condition, the output is always 1. That means what? In I6 you are giving 1. And then you take the last two combinations. You take 1 1 1 and here also 1 1 1. So in the selection line, if you give 1 1 1, this corresponds to I7. Therefore, this I7 gets a chance to the output. Now the 0 becomes 1 and 1 becomes 0. Again the output is always 1. If it is always 1, f equal to 1. Now when the selection lines are 1 1 1, 1 1 1, the output is always 1. That means what? Here output is always 1, but this 1 is coming from where? I7. So if you give 1, then this 1 will appear here. Therefore your I7 becomes 1 and I6 is 1, I5 is d, I4 is 0, I3 is 0. What about I0? I0, because this 0 0, all 3 zeros, right? Okay, this all 3 zeros, that means I0. I0 gets the input of d. Therefore this is d. And what is I1? 0 1 0, d bar. This is d bar. And okay, wait a minute. Am I done mistake? Any mistake? I'm sorry, it is D, right? I did a mistake. D, because it's here. This is D, okay? For 0 0. Okay. For 0 0 1, 0 0 1, that is I1. I1 also gets D. Therefore, for I1 you have to give D. And I2, I think D bar. I2 0 1 0. For 0 1 0, D bar. So D bar. Therefore D bar, sorry, D bar 0 and then 0, right? 3 and 4 gets 0. 5 is D, 6 is 1, 7 is also 1. So this is 8 by 1 max. Okay, therefore how will you implement? You just look at the function, Boolean function, and look at the number of variables in the Boolean function, and from that you take number of variable minus 1 to the data inputs here, data inputs, and one variable, sorry, only one variable to the data inputs and n minus 1 variable to the selection lines. Okay, and the important point is, notice that this if I write A, B, C, D, this A is called MSB, most significant bit, and this D is called least significant bit. This D is chosen for data input lines, and this A is given to the highest significant bit. Okay, so therefore this is S2. Look at the suffix 2, higher order bit, and this B is given to S1 and C is given to S0. Don't change, reverse the order. Okay, so the first variable A must be connected to selection input S2, and B must be connected to S1, and C must be connected to S0. And the values for the data inputs are determined from the truth table, from this truth table. Okay, so for example, if A, B, C is equal to 1, 1, 0, 1, 1, 0 means it is 6, right? Binary representation of 6. That means I6th input. So go to there, I6th input is 0, 1, 1, 0. Now you go here. Oh my god. What did I do? 110. Where is 110? Yeah, it is here. I'm sorry. Yeah. Now you have 110 here. So you have 110. For 110, 0 becomes 1 and 1 becomes 1. Irrespective of this 0 and 1, the output is always 1. And this 110 corresponds to I6. Therefore, I6 is connected to 1. That's it. So like that you can find out the every combinations. So therefore, this 1 is applied to 6th input of your multiplexer. I6th input of your multiplexer. And here this binary constants 0 and 1 represents two fixed signal values. And when I say if you use integrated circuits, in electronic circuits, when I say 0, this 0 corresponds to signal ground, that means 0 voltage. And this is logic 0, right? Logic 0 corresponds to 0 volt, right? And maybe logic 1 equivalent to some power signal, okay, depending on the technology. For example, it may represent 5 volt or 3 volt, like that. There are many ways, okay, ECL, TTL, like that. There are many technologies, CMOS technology, like that. So based on the technology, the value can change, but let us assume it's a 5 volt. So when I say logic 1 in electronic circuit, it is nothing but 5 volt. And logic 0, it is nothing but S0 voltage. This is called something called a positive voltage, as a positive logic representation. Okay, so that's how one can implement a given Boolean function using multiplexer. Okay, so let me stop here. In the next lecture, we will continue from here. Thank you very much.